read in the IB syllabus that the student should be able to explain the origin of atomic energy levels in terms of the electron in a box model. And that's what I've done on the previous video. Now here in the teacher's note it says that the model assumes that an electron is confined to move in one dimension by a box. The de Broglie waves associated with the electron will be standing waves of wavelength 2L over n. We've done that, I showed that to you, but it says here that the student should be able to show that the kinetic energy AK of the electron in the box is equal to n squared h squared over 8 times the mass of the electron times the length of the orbit squared, or the length of the wave squared. The n is the principal quantum number, and I wanted to show you how to get this. It says here that students should be able to show that the kinetic energy is equal to this. So here's how you can show it. And it is a playing with the equations. Now you might not like playing with equations. I like it, but after few hours of this, your head starts to hurt a lot. So here we have the electron being a standing wave around the nucleus. The electron has a certain kinetic energy, and it's orbiting the nucleus a certain radius away, and we want to find out the kinetic energy of that electron. So there are three ideas that we're looking at here. One of them we have here. That's the idea of the standing wave. So that's the relationship for the length of the wave, or the length of the box, I guess you could say, and the wavelength of the electron. And later on you will see that we'll need the wavelength squared. So here I just worked out that the wavelength squared is equal to 4 times the length of the orbit squared divided by the integer n squared, where the n is the quantum number. Again, where the n comes from, that the length of the wave has to be an integer multiple of half of the wavelength for it to be a standing wave. Here we have the idea of a kinetic energy of the electron, so the familiar 1/2 mv squared, and then we'll come back to this just basically at the end of the calculation. So what we have now is this this relationship for the wavelength squared, and then let's go over here. Here we have the old relationship, waves being particles. So the Planck's wave energy, h times f, equal to Einstein's mv squared. Now, what I want to get from this is the momentum of the particle squared. You'll see why. So here I am basically, I want to get rid of the frequency, and I want the wavelength to be in the relationship. So I'm substituting v over lambda for frequency. Then I can cancel out one of those velocities, and what I get then is this relationship for the momentum of a wave, so to speak. So the momentum equals h divided by lambda. Now I want momentum squared. So here I just square it, and then for the lambda squared, for this value right here, I'm going to substitute into it this value right here. Lambda squared equals 4L squared over n squared. So when I substitute it into the lambda here, we get this relationship in here, which can be then simplified to this. So momentum squared equals n squared times h squared divided by 4L squared. Now, I'm sorry that my n and h look very similar to each other. I'm trying to make the n, this leg a little shorter than on the h, so that's how you can distinguish them. So let's go back to the energy. That's what we want, and then we'll substitute into the energy this formula right here for the momentum squared. So here we're at the kinetic energy. Kinetic energy 1/2 mv squared. Now you can see the momentum is starting to come up here. So what I'm going to do is that I need momentum squared in here because that's what I will substitute. So I need another mass of the electron multiplying this. We can do that basically this way. So multiplying anything by 1 doesn't change anything. So mass of the electron divided by mass of the electron gives us 1. And I'm going to multiply that whole relationship by 1 in that form. So if we do that, we get this, that the kinetic energy of the electron is equal to 1/2 and the momentum squared divided by mass of the electron. And now we're just going to substitute for the momentum squared this relationship right here. So we do that. We stick the value in there. So for the momentum squared, I substitute the n squared, h squared over 4l squared, and of course that gives us this value right here, which is what we want to find out. That the kinetic energy is equal to of an electron confined in this box, or an electron wave being a standing wave around the nucleus of an atom, is equal to n squared, h squared over 8 times the mass of the electron times the length of the orbit square, where n is the principal quantum number, so an integer 1, 2, 3, and so forth. Another thing I wanted to show you here is that this L is the length of the orbit. In this case, if it's a circular, you can think of it as a circular orbit, it's given by 2 times pi times the radius of that orbit squared. So you could substitute that relationship there, and you could be finding the radius of the orbit. How far the electrons are positioned away from the nucleus.